Hello and welcome to the Biology Chapter 2 first lecture. We're going to be looking at the chemistry of life or living things. Keep in mind that in the first chapter we were talking about the organization of living things and how we have living things are organized in levels of organization where you get enough atoms organized the right way, you can build these molecules that make cells. And then you have cells organized the right way, you can make tissues, then tissues can make organs, and so on to get an organism. And this is universal. All organisms do this way. So we need to look at the very beginning level, which is the atomic or chemical level of organization. To do so, we need some basic understanding of what an atom is, how they work. Keep in mind that structure determines function in biology. So because something is built a certain way, it can do a certain job. It's no different for molecules and atoms even. The way they are structured determines what they are able to do. So we need to understand what goes into their structure so we know a little bit more about them, so we can understand why they can do what they do for living things. So first off, atoms. We all know what an atom is. It's a basic unit of matter. Okay, everything that matters is made of atoms. There are multiple flavors of atoms, and we call those elements. In that different atoms of different elements have different properties or characteristics. So for a basic atom, let's do helium, which is number 2 on the periodic table. Its atomic symbol is He for helium, and that atom itself is made up of smaller subatomic particles. So sub means like a submarine goes under the ocean, so subatomic means smaller than the atom. At one point there was some thought that maybe atoms were not divisible. That's in fact, even that word atom comes from the Greek word atomos, which means indivisible. But we know that it is divisible into these smaller particles, and these particles in turn are made up of other particles. But we're not going to go there, okay? We're going to stick with the basic atom, all right? So this is probably a review, but atoms are made of protons, neutrons, and electrons. They are not all the same, right? They have different roles, they influence different things, they're found in different places, they have different masses. So let's look at this. If we take our helium atom and we want to draw this, we're going to make the center of this first, which is the nucleus. And in that nucleus, it really doesn't look like this. We're just going to use a bunch of models for this, which represent it fairly good, but in reality is not really like the real thing. More on that later. So in our nucleus, we will have protons and neutrons. They will be in the nucleus here, and protons are positive. They have a positive charge. Neutrons are neutral. Like your car, you put it in neutral, you hit the gas, you don't go anywhere. Well, neutrons do not have a positive electrical charge or negative electrostatic charge. They're neutral. They don't respond to it, and they don't influence that. But your positive protons are in the nucleus with your neutrons. So because helium is number 2 on the periodic table, it's the second one, it tells me that it has 2 protons. Now, how do I know that? The atomic number, the number in the periodic table, tells me how many protons are in the nucleus. So hydrogen's 1 proton, helium is 2 protons, lithium is 3 protons, and so on. So you get up to like oxygen, it's 8, has 8 protons. So what that means is that the number of protons determines which element it is. If I could change the number of protons, I could change which element it is, which is what happens in a nuclear reaction whenever you have nuclear fusion, like fusing 2 hydrogen atoms together to make helium in the sun. That's what powers our sun. Or fission, which happens in the nuclear reactor, where you take some other large element and you split it into two smaller elements, like when you do uranium, uranium would split into like thorium and some other things, right? This breaks apart. Either way, you're messing with the nucleus and the protons specifically, and that is a nuclear reaction. Okay, we are not going to deal with nuclear reactions, so we don't get to mess with protons. We're looking at chemical reactions, which only are going to deal with the electrons. Right? So let's finish up on our nucleus and then talk about that. Okay, I'm going to add my 2 neutrons here. You can vary in your number of neutrons, and it doesn't influence a whole lot here. We'll talk about that in a sec. All right? Your electrons go in this area around here that we call the electron cloud. Electrons have a negative charge, so I'm actually going to use a little e with a negative. And in this particular model, and on most atoms, but there's some exceptions, if I have, let's say, 2 protons, I will have 2 electrons. If I had 6 protons, I'll have 6 electrons. That should be balanced. It can become unbalanced if you gain or lose electrons, which is totally possible. Because they're not here locked in the nucleus, they're not held together by that strong nuclear force that the protons are, then they can be gained and lost. They can do some different things, right? So the electrons are out here in the electron cloud. Okay? Collectively, these particles are known as subatomic particles. They're smaller than the atom itself. Remember that the elements are determined, what element this is determined by the number of protons. If I could add another proton, this wouldn't be helium, it would be lithium. It'd have different properties. The periodic table is organized 1 through 100 and something according to the number of protons. All right, some variations on this, okay? So let's say that helium, somewhere along the way, loses an electron. Now, helium in real life probably won't do this, but we're going to use helium as our example. So let's say, oh no, I lost an electron. Okay, how does that change me? Well, one, because you change the electrons, you're going to change how chemically active something is. Electrons totally influence how reactive you are, who you're going to react with, how you're going to react, how much you're going to react. It's all in the electrons. We're going to spend a lot of time talking about that. Right? Notwithstanding, we have a problem here, okay? Or a situation. We have 2 positive particles in this atom and only 1 negative particle. So we've got +2, -1. Overall, that gives me 1 + 1 charge that's not balanced out. At that point, this whole atom obtains a charge. It becomes charged. It has an overall positive charge. So I would write that as He plus. Okay? You sometimes might see He plus, you might see Cl minus, something like this. These collectively, whenever you see this positive or negative symbol next to an element's atomic symbol, that means that it has a charge. It is holding an overall positive or negative charge. Now, most don't exist this way, but many can or sometimes do. Either way, those are called ions. Let me erase them. Okay, these are ions, right? This is just a charged particle. And there's some ways for determining whether or not if some atoms meet up, if they're going to ionize or not. There's things that influence this. What we need to understand is that whenever you see these pluses or minuses on something, it means it's an ion, it's a charged particle, right? Cations are positively charged ions and anions are negatively charged ions. You don't necessarily need to know that, but that's how that terminology works, right? So this is one variation on our plain atom here. If we lose or gain electrons, which is totally doable, we can go ahead and shift our charge and become ionized. The other thing that can happen, which I mentioned earlier, is you can vary in your number of neutrons. Right? You can't change the protons. No doing that unless you have a nuclear reaction. But the number of neutrons naturally varies in an element. A really good example of that is hydrogen. So hydrogen is number 1 on the periodic table. Right? Most common material around. Right? Use it to make water and all sorts of good stuff. So hydrogen, most hydrogen, exists in the form of what we call hydrogen 1, which means it has the mass of 1 in its nucleus. So really all it is a positive proton. I'm just going to use a little plus symbol here. And it has 1 electron going around it. It has 1 particle in its nucleus, hydrogen 1. Okay, that also represents your atomic mass because protons and neutrons each have an atomic mass of 1. Electrons are really super duper tiny, and so we don't even really count their mass most of the time. It's 1,000th of that of a proton. I digress. Hydrogen 2, or H2, is, because it's hydrogen, it only has 1 positive proton, but it also has 1 neutron, and still our electron. And there also exists hydrogen 3, which has 1 proton because it's hydrogen, and it has 2 neutrons, and still our same electron. Okay? So these are considered to be isotopes. An isotope and an ion are not the same thing. Ions change the number of electrons, giving you charges. That will influence you chemically, how you behave and how you react, because electrons are what determine how you react, because they're on the outside. Right? Isotopes do not change how you behave when you interact with something chemically. If I wanted to make water, I could make water with this hydrogen, or this hydrogen, or this hydrogen. They would behave the same. Okay? With the caveat that this is increasingly more massive. And some isotopes are radioactive. Because there's too many or too few neutrons in the nucleus, they become unstable. Right? H3, hydrogen 3, which is also called tritium, is radioactive. It's used in glow-in-the-dark watch dials and gun sights because it glows. And it's also used as a precursor in a nuclear or atomic bomb. So there's not a lot of this lying around. There's a whole bunch of this. There's a small amount of this naturally occurring in the environment. And that's what an isotope is, right? We vary in the number of neutrons, our masses. We don't vary in how we act. In ions, we vary in the number of electrons, or we gain or lose them. And that is when we get a charge, and that makes us act a little bit different, right? It's all in the electrons, okay? Electrons totally determine how you're going to interact with other atoms. There's a special term for this. If I draw my, let's say, lithium, it's number 3. I'm not going to draw the subatomic particles. We know it's number 3, so it has 3 protons. So it should have 3 electrons. So we start to put some electrons in here, and I'm going to draw these layers. Okay, these are not orbits. This is a nice model. This is called a Bohr model, B-O-H-R model. This is a way of drawing an electron now, or an atom. Now, really, this should be like incredibly tiny. Like if you go to the football stadium and put a skittle in the middle of the football stadium, that would be like the nucleus. And then you'd have like an itty bitty little, I don't know, small BB type thing zipping around at like the speed of light somewhere, not on the track perfectly, but somewhere around there, right? That's more realistic than this is, but we can't draw that. So we're going to go ahead and we're just going to use these concentric rings. It is not like planets around the sun. Okay? This is called a Bohr model, but it's a good way of representing things. The reason we put these rings is these represent energy levels or shells. And the main thing that we need to understand for this course is that the outermost energy level or shell really represents what the atom presents to the rest of the world, right? So when we want to determine, hey, how are you going to act, we look at the outermost energy level. And we see we only have 1 in this energy level. Now, normally, we can hold a total of 2 electrons in the first one, and whenever it gets full, it's like, I'm happy, I'm full. Then we start filling up the second one where we can hold 8. Now, I would really love to have 8 to fill this up, or have a full outermost energy level. Okay, that makes me inert or stable when my energy level on the outside is full. Okay, so when you hear that something is chemically not active, or it's inert or stable, it means that I've got a full outermost energy level, right? That doesn't always happen. If it's not full, then you're active. You're ready to react. You're ready to start to, hey, you want to swap some electrons with me, or you want to interact with some electrons, right? So this guy's ready to interact right now, right? This outermost layer, and this is really important, is called the valence level. Valence level. This is a super important idea, all right? So the valence level of the electron determines how an electron is going to act chemically, right? The protons don't do that. The neutrons don't do that. This inner level does not do that. Only this outermost level determines how you're going to act. It's what, unlike people, it is what's on the outside that counts when you start to talk about atoms, right? Because that determines who they're going to act with. Is this lithium going to interact with oxygen? Is it going to interact with another metal? How is it going to act? Well, we can predict that looking at that outermost valence level, right? And it's really what guides that. Speaking of which, you can join things together and make compounds like water, right? Water is a compound. It's H2O. It's always H2O. If I change H2O, it's not water anymore. For example, hydrogen peroxide, the bubbly stuff in the brown bottle that your mom puts on your cut and it hurts, and you say, Mommy, make it stop. Okay, that's H2O2. It's not the same. You don't have the same chemical formula. If you have the same chemical formula, you're the same material. If that varies, you're not the same thing. So if that varies, if that chemical compound you made is not the same thing. So how do you make a chemical compound? How do you get 2 or more atoms to join together? You need some sort of bond or a force of attraction. A bond, don't think of it like it's not like nailing something together. It's more of some sort of field force of attraction, like almost like magnetic attraction. Might be a decent way of thinking about it. It's not magnetic, but that might be a good way of envisioning it. So the first type of bond we want to talk about today is an ionic bond. So in order to make an ionic bond, what must you have? Ions, all right? So I need some ions. What were ions? Ions are charged particles. So how do we get a charged particle? We gain or lose what? Electrons. Okay, if you can't gain or lose protons, you're nuclear reacting. We don't do that around here, right? But we can do chemical reactions. And so when some atoms meet up, they can gain or lose electrons. Let's go back to our lithium that we had. We said that lithium had 1 valence electron. Okay, I'm going to represent that with a little dot. This is another way of drawing atoms. It's called a Lewis dot diagram, and we just put little dots around the outside of the atom to represent the number of electrons it has on the outermost layer. The valence layer, because that valence layer is really what matters on how reactive it is. Right? And let's say it meets up with some fluorine. So fluorine has 7 outermost electrons, and it would really like to have another one. Fluorine also has a really strong pull, and so it can actually rip, if these two meet up, it can rip that electron out of the electron cloud of this lithium away from that nucleus and pull it over to itself. It's got really strong electronegativity, really strong pull. Okay, if that happens and they meet up and that transfer is made, then hey, fluorine's now full and it doesn't want to really interact. Lithium no longer has that outer valence electron. It's now got that inner layer, which was full. So they like chill out. They're like, all good, we're stable, we're satisfied with having our valence level full. But something else happens. Because the lithium lost a negative electron, overall it now has more positive protons. It obtains a positive charge. Fluorine gained a negative electron. It obtains a negative charge. So what happens? They've ionized at this point. And